All right, folks. So what I'm going to do here is really kind of flip things up from how I've done it in the past. I'm actually just going to show some practice problems because I found that with myself at least, and I've heard this as feedback from other teachers, that seeing the process on how to do things kind of helps you get an idea of how the heck do you approach some of these and kind of gives you a feeling for what's normal and maybe what's not normal, because this probably will feel a little uncomfortable kind of doing some of these, at least in the beginning. So really, I'm just going to go through and do a few problems, and I encourage you to follow along, stop, make sure you can do the algebra. You can actually get the same numbers as me on the calculator. Bonus points, sure, if you find a mistake I've made. But also, like, write down or box or put down questions you have, like, what the heck did he do here? So really, I've just found some problems from like page 42, 43, 44 in our textbook, and I'm just going to go for them. And so what I've done here is I really have just rewritten our main three equations that's on our AP equation sheet. And I want to mention here that x doesn't have to be x, it could be y. Something's moving up and down instead of left to right. And I also want to just throw out that soon this acceleration thing is going to be g, where g is gravity. It's the acceleration due to something falling, and everything falls at the same rate. And so acceleration due to gravity is 9.8 meters per second. And so that's actually on your AP equation sheet. I'll show it really briefly here, that we can find on our website or on our Google Classroom. So here's kind of our three equations that we're using typically right now. And then way up here on the front page, a bunch of constants. Acceleration due to gravity, 9.8, and they put it meters over seconds squared. So you can totally find it right there, just kind of as a heads up, all right? And where are we now? There we are. So again, I just have my equations, and really we're just going to look at this first question. So I wanted to speed up a little bit because some folks said I was going a little slow there, and then you can just kind of pause, rewind as need be, all right? So a car accelerates from 12 meters per second to 25 meters per second in 6 seconds. What is its acceleration? So it's asking how quickly is it speeding up? And then it also says, how far did it travel? So it's asking for two things here. Really, this thing is probably x. All right, maybe I'll use a different color that shows a little better. X, and then here's a in the x direction. Now, this 12 meters, that's what we started with. So that's going to be our Vx, not our initial x velocity, 12 meters per second. And it says that it ends up at 25 meters per second. It says it takes 6.0 seconds. So really, I always write down what's known. All right, so I'm trying to model the process, really. All right, assume acceleration is constant. All of these equations are like trash if we have an acceleration that's changing. So you won't ever actually encounter that, okay? So it's asking first, what is the acceleration? All right, and then it's saying, how far did it travel? So let's just go for it in that order, okay? That's kind of how we'll approach it. So we want to find the acceleration. So we want to find the acceleration in the x direction. And we want to figure out which of these equations should we use. Really, this is kind of the name in the game. So the process that I want to state first and foremost, kind of up front, is look at what you're given, organize it. Sometimes just reading this and staring at all the information here doesn't really help. Writing it down organizes it. It kind of lets you see what you have to work with. Once you see what you have to work with, which of these equations up here then is really going to get me what I want? So I'm looking at all of these. This has a in it. This has a in it. This has a in it. So okay, looking at the a, what we're trying to find doesn't really help there. Okay, but which one has time and both velocities? In other words, like, which has the stuff that we know? So this has both velocities and time, and it has the thing we're looking for. So right off the bat, I would say probably use equation one, in all honesty, because it has the three things we know, one thing we don't know. Since we do not know x here, if I use this equation, I don't know x, and I don't know a. Well, I have two unknowns. I couldn't solve this, okay? Let's looking at the other one. We know both of the velocities. They're given, all right? I'm trying to find acceleration, but I also don't know x. This also has two unknowns. So really, these don't work. The only one that works is equation one, okay? So finding the acceleration in the x direction, well, let's use equation number 1. Okay, so that's kind of the gist. So all I'm going to do is I'm going to rewrite it. The final velocity is equal to the initial velocity plus the acceleration times time. Now, looking at what we know here, I would caution you against plugging in all the numbers immediately. The reason I say that is I make lots of mistakes, like writing numbers personally and then like putting them in the calculator, for instance. So I do it all with just algebra, with just symbols, and then I plug in numbers at the very end. So I'm going to just get this A alone here. So there's a couple ways that your math teachers probably said it. A lot of people say that like math is kind of like this teeter-totter and you want to keep it balanced. So if you go and you mess it up one way, well, you have to kind of balance it back out, right? And so one way that I bet some of your math teachers would say it is, well, subtract Vx from this side. You also have to subtract the final or the initial velocity from this side. So then you would have the final minus the initial x velocity is equal to acceleration times time. The other way that I personally was taught this is, well, I'm just going to take this thing and I'm going to subtract it over to that side. That's the other way. They both kind of really give you the same result, but just whichever way makes more sense to you. Similarly, I want to get acceleration. If I divide both sides by time, well, I have to divide this whole side by time as well. It ends up being that, well, the times cancel. And so I have this handy equation now. The final velocity minus the initial x velocity divided by the time gives me the acceleration in the x direction. So now what I can do is I can plug in the numbers. So 25 meters per second minus 12 meters per second. Well, that's 25 minus 12, that's 13. It took 6 seconds. That gives me, if I do 13 divided by 6, right? Well, now I have 2.17, and the units are going to be, well, meters per second up top divided by seconds. So meters per second divided by seconds. Now, following significant figures, though, I see that 25 has 2 sig figs, 12 has 2 sig figs. So, and then I'm dividing by 6, which has 2 sig figs. So combining these two, well, I have a number with 2 sig figs on top. That's 13 divided by 2 sig figs on the bottom. My answer should have 2 sig figs. So really, I'm going to have that my x acceleration is 2.2 meters per second per second. All right, that's kind of the whole idea on how to get the first part of this done. We looked at what we knew, looked at our equations, said which ones work, which ones don't, and then let's go with the easiest one that should work. All right, so now let's find time. Find t. Now, which equations do we want to use? Well, we want to find out how, or sorry, we're not finding t, we're finding x. I'm tripping, sorry here, folks. So finding x. But let's figure out which equation to use. Well, use equation, well, number 1 doesn't have x in it, so that one's out. Let's look at equation 2. It has x. What does x not? I didn't do anything with that down here. I didn't talk about it down here. Well, I did say earlier in some notes that we get to typically pretty much always call where it started at 0, which is kind of neat. You could call it 5 in all honesty, but then if you used equation 2, you'd have to plug in a 5 here, and then you'd have to like deal with that in the equation. So we can call this 0 meters, and that kind of simplifies things, right? So if we think about it, we know where it started. We know the initial velocity it's given. We know the time. We now know the acceleration from down here. And again, we know the time. So equation 2 would work. Okay, now is that our only option? Or could we use equation 3 as well? Well, do we know how fast it's going at the end? Yeah, it's going 25. We know that. We know the initial. Again, we know the acceleration. And we know that this x naught is 0. So the only thing we don't know here is x. So we could use equation 2 or 3. I would encourage you to use the one that you think is easier. Since we're trying to find how far it traveled, x, I would argue that equation 2 is easier because it's just going to give you x automatically right at the end. But we can use both. We can kind of try it, all right? So I'll kind of split my page down the middle-ish here. Let's do it in purple, actually. I like purple. So there's that. and we'll just kind of go for it, okay? So we have x, our displacement is equal to the initial displacement plus the initial x velocity times time plus 1/2 the x acceleration times time squared. Well, we know that we get to call where it starts 0, okay? And now I can literally just plug in. So it traveled this distance that's equal to 12 meters per second times my 6 seconds plus 1/2 my acceleration of 2.2 meters per second per second. That's the same thing as meters over seconds squared, mind you, times our time squared, which is 6.0 seconds squared. Now, the neat thing that's going to happen that I want to show is that we're taking 12 timesing it by 6. Well, that's 72, right? But we're taking meters divided by seconds and timesing it by seconds. So I'm timesing by seconds, but I'm dividing by seconds. The seconds cancel out. So this thing is going to have units of meters, which checks out because x should be a length, how far it's gone. Similarly, if I'm squaring seconds, I'll have seconds squared, right? Well, seconds squared is going to cancel if I'm timesing this thing by meters over seconds squared. So this thing on the right is going to have just units of meters as well. So the units kind of check out. So you do need to be including the units with this. Now, when I just did the math, I got x is equal to 111.6 meters, but following sig figs, this has 2, this has 2, this has 2, this has 2. This 1/2 kind of has infinite, like we talked about earlier. So my answer should actually have 2, really, in all honesty. So I would round this to 112 meters, or actually 110 meters with no decimal, okay? Now, I'll tell you, if you follow your algebra correctly and you use equation 3 properly. So if we use equation 3 here, and actually I'll just write use equations 2 or 3, which is kind of neat. There's more than one correct way to do it. We have that this final velocity squared is equal to the initial squared plus twice the x acceleration times our change in displacement, all right? Now, this one's more of a pain, as you can probably tell already, because x isn't alone on one side. So we'll have to do some algebra to get x alone, okay? So what we would do is we would subtract this vx naught over. So we're going to have this final velocity squared minus the initial velocity squared, and then we would just divide by 2a, all right? So I'll kind of do that in one fell swoop. And I would encourage you to see if you can do it in the couple steps. And if you have questions, ask me in class, all right? So I'm going to end up getting this thing because I just subtract that over. And then to get this x alone, I would just divide by 2 times the x acceleration, and that would give me x, all right? So then I would plug in. I'd have 25 meters per second squared minus this 12 meters per second squared. And then I would be dividing that by twice our acceleration of 2.2 meters per second. And I'll write it as second squared just so you can kind of see why this works really, okay? Because what this ends up becoming then, if I go down a little bit more, is I have 481 meters squared over second squared. Because when we square this thing, it's squaring not just the 25, it's squaring the meters per second. So that's divided now by, and well, 2 times 2.2, that's 4.4 meters per second squared. So now you can probably see why I wrote it this way. We have second squared up top, second squared up bottom, those cancel. Meters squared up top, that 1 goes away, and then a meters down here. And this ends up becoming 109 meters. But again, rounding for significant figures, because 4.4 has 2 in it. Well, now I get 110 meters is x. Kind of wild that doing it a totally different way, we get the same answer on both sides, right? So kind of neat. So overall, the process, look at what the heck you have to work with, write it down. Let's look at our 3 equations. These are really our tools, and there is a lot of deep kind of concept behind it, but it's based on calculus. So I'm trying to kind of glaze over that so we can kind of start using the tools rather than struggling to learn calculus when you don't need to learn calculus. But then once we kind of figured out which equation to use, then it stops being a physics problem and it's now just kind of a mathy thing, okay? So let's look at another one. A car slows down from 20 meters per second to rest. So that means it ends at 0 meters per second, right? And it's slowing down. So if it's slowing down, that means my acceleration is going to be a negative value. It's getting slower and slower. It's not going to be a positive acceleration. It'll be negative. So here's my initial velocity then, and they give me the distance, which is kind of neat. So we know the initial velocity is 20 meters per second. We know the final is 0 meters per second. We know how far it's gone is 85 meters, and we know that we get to define where it starts to be 0, all right? It's asking what the heck is A? So we want that thing. And so what I've done is I actually went and I rewrote my equations here so we can kind of see them. This is really the trick and the tip that I would recommend, unless you want to memorize them and think really, really hard. But let's look. So all of these have A in them. So that doesn't help because we want to get A, right? So which of these then can I use to get my answer? So let's look at the first one. Well, we know how fast it's going in the beginning and in the end, right? Do we know the time? No, they don't tell me how long it took. So I have two unknowns here. I don't know A, I don't know T, I don't know the acceleration or the time. So this one is out. This one does not work, all right? Let's look at our second one here. Well, we know it went 85. We know this thing is 0, so we know those. We know how fast it's going in the beginning. Again, we do not know time. So again, I have two unknowns. I have time here and time here. This one's out. So hopefully this third one works. Do I know how fast it's going at the end and at the beginning? Yes. Do I know the acceleration? No, that's what it's asking me to find. Do I know how far it's traveled? Yes. We're going to use that one. All right. So we'll use equation 3 for this. Okay. There I am. So use equation 3. All right, so here we go. We have the final velocity squared is equal to the initial velocity squared plus 2 times the x acceleration times how far it's moved. Now, we know that it ends at rest. So really, the final velocity, this thing is 0, right? Because that's this thing right here, okay? And then we know that we get to define the starting point as 0. And that's almost always the case, but not always, okay? So now I need to find the acceleration. Well, now we could rewrite this if you're not a super visualized kind of mentally person. We have 0 is equal to the final or the initial velocity squared plus 2a in the x direction times x. That's it. And we're trying to get a again, right? So I'm going to subtract this v x naught over this initial velocity. So I'll end up having negative the initial velocity squared is equal to twice the acceleration in the x direction times x. And I want a alone, so I'll divide by 2 and I'll divide by x on both sides. So really I have negative, the velocity in the beginning squared divided by 2x. That'll give me my acceleration. So let's just plug in and I end up having negative 20 meters per second. Now this is important. We have to actually put some parentheses around this because if you squared it like this, you're going to get a positive answer, right? But that's not the case. Where it's negative, whatever this thing squared is, okay? So then we're doing divided by 2 times 85 meters, okay? Now, I can tell you right now what this is going to give me is negative, because we have a minus here, right? 400 meters squared over seconds squared divided by, and then 85 times 2 is 170 meters. Well, I can see right here that we have a meters on top because of meters squared goes away, and then this one goes away. So we're going to have meters over seconds squared, which is kind of neat. So my answer ends up being negative 2.35 meters over seconds squared. But again, for sig figs, right? Now, this is kind of the weird one. This 400 is based from this 20. 20 only has one sig fig in it. So really my answer should just be -2 meters per second squared, or a way that makes a little more sense, 2 meters per second per second. That is our deceleration. That's how much it's accelerating opposite the direction it's moving. Okay, so there's that one. Awesome. Now, I want to pause on this one for 21. This is what I want you to do. All right. Again, keeping in mind the basic flow of this really is figure out what the heck you have to work with. All right. Based on what you have to work with and the thing that you want, which equation is most appropriate. Once you've figured out, or hopefully figured out, or have an idea, or if you don't have an idea, try all three and see where you end up having two variables, two unknowns, right? And then you go through and it becomes this math thing where you do some algebra, you plug in a couple numbers at the end, carry the units along, and the units should make sense, right? If it's a distance, well, you should get meters. If it's a speed velocity, it should be meters per second. If it's an acceleration, it's how much velocity is changing over time. It'll be a meters per second thing, or a meters per second squared, all right? So pause here. I want you to do 21, okay? And I'm going to tell you that what they give as the final kind of answer should be 150 meters, okay? It should be 150 meters, except actually for sig figs, because our textbook doesn't really follow sig figs, the awkward rounding you would get is 200 meters, okay? So that's because of sig figs for how far it goes, okay? So do that one, and then so pause it here, do that one, and then let's go on to 26. This is one that we did together, or I mostly did it together, depending on which period you're with me. So I'm just going to walk through this one. I'm actually not doing this from scratch. So we have a car that's going at some velocity, some speed, actually, because it's a speed, not velocity, because they didn't say north, south, east, west, up, down, whatever. They gave us no direction. But the awkward thing here is they give us kilometers per hour, and that does not work. We got to have meters per second. Otherwise, it doesn't really make sense. So we'll have to convert that. It's a pain, and I'll show it. The front of it compresses, and the driver comes to rest. That means that the final speed is 0 meters per second, okay? And it travels 0.80 meters. So that's how much it crunches, and the driver actually moves, all right? 0.8 of a meter, so 80 centimeters, all right? Which is actually a pretty significant amount. What's the average acceleration? And then it says, what is that in G's? So I wrote down all the things I know. We're given how fast they're going in the beginning. They stop, they travel this far. We call the initial position 0. We want to find A. So just thinking of that, without even converting, we want to find A. Let's look at the first one. Well, we know how fast they're going at the end, that's 0. We know how fast they're going at the beginning. Fantastic, great. We want to find A. We weren't given a time though. So equation 1 doesn't work. It's garbage. We have 2 unknowns, so we can't solve it. Bummer, awkward. Equation 2 ends up being the same. We know X, we know X naught, we know the initial velocity, but again, we have time and acceleration here. We can't use this one. Hopefully the third one works. And if we find out and take a look, we know that it stops. So that's 0. This is this 90 kilometers per hour. We want to find A. They go 0.80 meters. We totally know that one. We just have to use this. The only hiccup is converting kilometers per hour to meters per second. So I'm going to show it here. I used to do it one way, the way up top when I taught chemistry here. I'll try and do it this other way, but they both mean the same thing. So we start with this kilometers per hour. And I just want to get rid of kilometers first. Now you can Google it, how many meters are in a kilometer, but kilo means 1,000. Kilogram then means that there are 1,000 grams in a kilogram. A kilometer means that there are 1,000 meters in a kilometer. So really, I write it like this. And I chose this order. I could have flipped this. So the kilometers on top, the meters on the bottom. But if I do it this way, we end up seeing that, well, hey, kilometers on the bottom cancel with the kilometers on top. We're left with meters up top, and we want meters per second, which works. Now we need to turn hours into seconds. So I said that, well, I know in 1 hour there's 60 minutes, and I chose this order with hours on top because now my hour up here cancels with this hour down here that we started with. But then I'm in minutes. So to go from minute land to second land, I have to go and write in 1 minute, there are 60 seconds, and the minutes here cancel the minutes there. So the only units that are kind of surviving are meters on top and seconds on the bottom. And then I just did math, right? Like 90 times 1,000 divided by 60 divided by 60, no parentheses, you'll get 25 meters per second. Just as a heads up, I may write it this way just out of, I don't know, habit. It means the same thing. It's just a way that I can be a little lazier, I guess, and not have to write multiplication signs, but that's all it means. So now we know what it is in meters per second. We just have to plug it in right here. That's it. That's all we're going to do. And I've done it both ways. If you're someone that likes to plug in the numbers immediately, that's what I did on the left here. If you're someone actually like me, really, that typically likes to like do the algebra first and then get an equation and then plug in, here's how I did it on the right. So in the end, we end up getting that the acceleration is like 390 meters per second squared, and it's negative. And it's negative because they're slowing down. They're going from pretty quick, like 40 or so miles per hour, to nothing very quickly, right? They're traveling less than a meter and they're going to a stop. So this person is pulling a lot of G's, and you can figure out the G's by actually just taking their acceleration and dividing it by gravity, because G is 9.8 meters per second squared, or per second per second. And so you'll see that the units cancel. So G's is a unitless thing, really. So you get about 40 G's this person's pulling. So they're probably not doing too great, in all honesty. So rough. Now, last one, and this is actually kind of a harder one because this is something a little new, but it's kind of cool. So here's the gist. We have best rebounders in basketball have a vertical leap of about 120 centimeters. Now, centimeters can't be in that units, just like we can't have kilometers. We'll have to turn that into something else. But we want to find what is their initial launch speed off the ground. How fast are they going the moment they take off? And then how long are they in the air? So we want to find the initial velocity, but it's not in the x direction. This is in the y direction, right? We want to find their initial y velocity, and we want to find how long they're in the air. What's their hang time, right? So I threw in this great picture of Michael Jordan, freaking king, right? Chicago Bulls, heck yeah. But I just wanted to show this is really what it's looking at. We're looking at his vertical leap here. We're saying that, well, where he ends is 1.2 meters. Now maybe you're going, wait, no, they said centimeters. Well, just like the kilometer thing, centi means a 100th. So that means that 1 meter is 100 centimeters. So if I had 120 centimeters to go backwards to meters, if I had to take the decimal and go 1, 2, now it's 1, just like I have here, I would do the same thing. I'd go 1, 2, and then I get 1.20 meters. So that's how I actually did this. And we can see that, hey, he's starting, of course, on the ground. So with these equations on the sheet, they're all in X. We're just going to rewrite it with Y. That's it. That's literally it. So don't worry. Don't freak out. It's just, instead of left and right, it's up and down. Okay. So that's really it. That's all we're doing. That's kind of the new thing here, aside from keeping in mind that there's something slowing him down, right? Like he's fastest down here, right? Like down at the bottom, he's moving the fastest. But the farther up and up and up he goes, he slows down more and more and more and more until the very top of his vert, right? He actually pauses. There's like an instant where he's actually not moving. His velocity is 0. And the weird way that I would say to think about it is he's going the fastest at the bottom. Well, I guess we'll put it down here because that's the ground. And as he goes up, he's going up quick in the beginning, and he slows down and slows down and slows down and slows down. And then he pauses for literally like an instant, like a millisecond, but he actually does, because then he stops and turns around and falls back down, right? So at the top of his jump, or the top of you throwing something up, it actually stops because it has to turn around, right? It's the same thing if you were running left to right. If you're running over here, you have to pause to then turn around. So that's kind of just a conceptual thing. So we are given that y is 120 centimeters, but that's the same thing as 1.20 meters, okay? Just like how instead of x naught, we know y naught, we get to call this thing 0, all right? And that's all we're given. Like, what the heck? Now, what's the thing slowing him down, though? Well, it's gravity. So the acceleration now in the y direction is g, gravity. And it's this thing I showed. It's on your equation sheet. It's right here. Acceleration due to gravity. It's 9.80 meters per second squared. It's little g. It's so common. It gets its own special symbol, all right? So here we are. Acceleration is g, all right? And it's this 9.8 meters per second, or you could say meters per second squared. Now, something weird that I have to introduce here is that we're not doing this all just on a line, really, right? We know that we're in like a 3-dimensional world. And even before that, we're in a 2-dimensional world. And in this 2-dimensional world, we really have things going like in the y direction and in the x direction. And this is positive x, and you probably normally think this is positive y. That means that this is negative x and that this is negative y. So when we really think about it, gravity is always pulling down. So gravity is pulling in the negative y direction. Remember back to that earlier video, we talked about vectors. Acceleration is a vector, so it has a direction. And in the past, we've looked at all these, and we got some negative accelerations. We've gotten positive accelerations. Well, for this case, we have to keep in mind that as long as we're kind of framing this in the way that's intuitive, that you really think about it, well, gravity is going to be acting in the negative direction. If you want to be weird, you can totally call up the negative direction and down the positive direction, but then you have to like start changing your numbers and your values, right? That would mean that if this is 0 down here, he went negative 1.2 meters up, and then it just gets kind of screwy. So I would encourage you to not do things that way. I would probably just call that positive and this one negative, okay? So let's get through this problem and then we'll be all done, okay? There we go. So looking at this, we just said that at the top, we know he stops but to turn around. So that means Vy, all right, that's really what this means, is 0. He stops at the top before he turns around and starts falling back down. And we're trying to figure out Vy naught. We have no idea what the heck this thing is. That's what we really want. So we can look at these equations again and just think of them honestly like change the x's to y's. It is really that simple. So if we know, and we could rewrite them if we want, but just for sake of time's sake, for you really, let's look at the first one. Well, we want to find his initial velocity. So we know the final, we know he stops, we know acceleration is g. We want to find this thing. Do we know time? No, we weren't given time. So this one's out. We have 2 unknowns again. Sucks. Whatever. Now, do we know how far he travels? Yeah. We get to call this one 0. Yes. We want to figure out what his initial speed is. That's what they're asking us. Do we know the time? No. That's part 2 of the question. So this one doesn't work as well. So now let's look at the third one. We know he stops at the top. So we know this one. Do we know the initial? No. That's what they're asking us to find. Do we know gravity is what's speeding him up or slowing him down? Yes. Do we know how far he goes? Totally. Let's use equation 3. All right. So here we go. Equation number 3. And we have the final velocity squared in the, not x, in the y direction is equal to the initial y velocity squared plus twice the y acceleration times how far he's traveled. And we know that at the top he stops, so that's 0. We know that we're calling where he starts 0 on the ground. So really, we just need to solve for this Vy naught thing. That's it. So all I'm going to do is rewrite it once. So we have 0 is our initial y velocity squared plus twice the y acceleration times y. So if, again, I want to get how fast he's going in the beginning, I can just subtract this whole thing over to the left side. So now I have, there we go. So now we have negative 2a in the y direction times y is equal to the initial y velocity squared. We'll plug in our numbers. But the last thing to do is to get this thing alone, we just take a square root of both sides, right? If I square root this side, that cancels out with the squared. We'll square root this side, and that will really do it in the end, in all honesty. So we now have the square root of 2 times the y acceleration times y, and I have this negative sign in here. And maybe some of you are going, wait, you can't take a square root of a negative. Well, hang on, let's look. We have twice gravity, which is already a negative, and that's 9.8 meters per second times how far he's traveled, 1.20 meters. That is my initial y velocity, and we're taking the square root. That was the worst square root I've probably ever written, but that's fine. And we see that the negative signs cancel. So we have this double negative, it becomes a positive, and what we get in the end is that he's going 4.85 meters per second. All right. So that's how high or how quickly he's going when he first takes off the ground. And if you look here, we should have 2 sig figs, so that really would round to his initial being 4.9 meters per second, which is pretty quick. That's pretty quick takeoff, in all honesty. So now we want to find the time. How the heck do we do that? Well, we have to look back at these. Our third equation here that we just used doesn't even have time in it. That's why we used it. But now we could use really any of these, right? We know how fast he's going in the beginning. We know acceleration. We know that he stops at the top. Let's use this one to find time, okay? So we'll rewrite this one to find our time. Our final y velocity is equal to our initial y velocity plus our acceleration times time. We know that at the top he stops, right? So now we just have to get our t alone. So again, doing a little algebra here, we'll subtract Vy over to the left side, and then we'll divide by the acceleration. So negative Vy initial, our negative initial y velocity, divided by our acceleration gives us time, or in other words, the negative of our initial y velocity divided by gravity gives us our time. That's the other way you could have written it. And so all we have to do is negative 4.9 meters per second divided by negative 9.8 meters per second squared. Now, this is maybe a little weird. You're looking at it going, I don't get how the units work. It turns out that, well, of course, our meters up top and our meters on the bottom cancel. And then we have 1 little second that survives down here, okay? This little squared goes away. This second goes away. And what we end up getting is like 1 over seconds. That's the same thing as seconds, okay? So this really ends up being 0.5 seconds is his hang time, okay? So with that, write down questions, comments, anything that I can go over. But otherwise, that's it for kind of our rough and quick introduction to these equations.